Expectations sending you spinning? You are not alone. We generalized the previous result to a standard form that can be used for any normalized spinor. As we see, for this problem, we want for the most general normalized spinor chi, compute the expectations of the x, y, and z spin matrices, and of course the squares of those, and check that sx squared, sy squared, and sz squared is equal to the S matrix squared. So this will take into account a couple different algebraic forms, and of course the eigenvalues of S squared. Before we start, I'd like to mention that there is a free companion PDF available for you to follow along. You can access it using the link below. Stop number 1 on this journey, of course, we start with the x component. Of course, with the expectation value, since we're dealing with states and matrices and broadcasts and all that other fun stuff, we use the Dirac notation instead of the integral notation. Just be aware, slightly different, same concept. So with this, of course, like we saw last time, this Dirac notation leads us to the chi dagger Sx chi, where Sx was equal to h bar over 2 with the Pauli spin matrix of sigma x. Of course, we have some general standard form that is normalized, of course, for the chi state, so the chi spinor state. So we'll just say A and B and work our way through. The dagger, of course, means complex conjugate transpose, which is why we see that this is now a row vector with complex conjugate entries instead of a column vector. Here we see that sigma x is equal to this Pauli spin matrix, which we saw last time, and now it's just a matter of multiplying them out. So this blue matrix multiplied with this one here gives us another column vector with the entries switched, as we see from the multiplication. And now we're just left with the multiplication of this row vector into this column vector, which leads us to this result. This is easy to read, and we see something cool from it if we algebraically manipulate it slightly. Because we're assuming that these entries in the matrices are complex numbers, this A star B and B star A have a really cool connection if we write them in terms of the real part and imaginary part of the complex number. How do we do this? Well, let's take a look here. We know that by having a star, or rather, if we take the complex conjugate of a complex number twice, we undo the first one, and we end up with the same number. So we invoke two complex conjugates here, and what we're doing is form matching in a way, because this complex conjugate will undo this one, but also put it on A. But then we still have this outermost complex conjugate, so we have A star B, and then A star B again, but the whole thing is starred. If we make the substitution to Z a complex variable, which is what's going to happen when we A star B multiply the two together, it's just another complex number, we see that we have the form of Z plus Z complex conjugate over 2, thanks to this h bar over 2. With that, we know that this is the form of the real part of the complex number. So we say h bar real of Z. And of course, since we made the substitution of A star B with Z, we plug that back in and we see here. What's cool about this is not necessarily this one alone, but how it pairs with the next one. So let's check that out. Oops. So on to our next stop then. It's pretty similar, rinse and repeat. We kind of saw this last question, and it's very mechanical in application, or rather processing. So we just run it through with the y component. Everything's the same. The chi vector goes to the same thing, except now we have the y Pauli spin matrix, which is 0, -I, and 0. Multiply that through, settle it out. Be careful with the algebra. You could factor the I out here, which is what we do. And you see it's very familiar to the form that we had for Sx, except with some negatives and an I. Okay, well, if we unrationalize this and put I in the denominator, and that thus the -1 up here, we can now distribute this -1 and use the same method that we used with the dual complex conjugates to kind of cancel things out. And now we see that we're set up for a really fascinating substitution again with Z, just to highlight this. And we see that we have Z minus Z star over 2I. If this is the case, this is exactly what the imaginary part of z would be. So we have h bar imaginary part of z, but we made the substitution that z was a star b. So the whole point of doing this is that we see that with respect to x, we have the real part. With respect to y, we have the imaginary part. Pretty cool consolidation there. What do you think is going to happen with the z part then? Let's check that out. Moving on to the third leg of this part one, we see that we run through the same process except for the sigma z, which is 1, 0, 0, -1. Again, we talked about some of the properties of this last time, so we'll just run it through. And then we see that we get a star a minus b star b. Well, that's just the magnitude of a squared minus the magnitude of b squared. Pretty easy, I would say. A little bit different than what we saw in X and Y, but remember a lot of these are measuring with respect to the Z-axis, so now this kind of makes more sense. That being said, we can move on to stop number 2 now that we powered through our problem checkpoints and found all the expectation values for j equal 1, 2, 3 or x, y, z. Good to go. That being said, we still have to find the squares, and if you remember from last time, this was relatively easy as well. So let's go ahead and run it through at least for one of them, and we'll just showcase how it's done. So we have a square here, and we need to write out that matrix squared. Again, if you want more of the algebraic simplification here, the PDF has it. But hindsight tells us that this squared matrix equals I, so that'll be really easy to deal with. Which we see here, when we multiply those two matrices, we get the identity matrix. We know that this times any of the vectors to the right give the same vector back, hence AB again. That being said, we can quickly move on, and now we see that A star, B star multiplied into this column vector gives us this, which is magnitude A squared plus B squared. But wait, we were told this spinor was any generalized general normalized spinor. So because it's normalized, we know that A squared plus B squared equals 1. Thus, we get back the same result we proved last time, which was h bar squared over 4. How cool is that? Using these methods, we can quickly prove it for the other ones as well. As you see, here's some of the work for the y. We'll go ahead and run through that, but at least you can see it. Again, you end up with the magnitude a squared plus b squared. Easy enough. Run that through, you get 1, and you see we get the same result. Z here, as you can see. Again, I wouldn't worry too much about it since you now know the insight to the square matrix for the poly matrices equals I. That's pretty easy, and that's capital I, not the complex conjugate, or the complex number, excuse me. But anyways, what we see here is that for all j equal 1, 2, 3, or x, y, z in this case, we see that the expectation is h bar squared over 4. Easy enough. Now we need to see what happens with the S matrix itself squared and compare the results for these x, y, and z squared expectations. So that being said, we successfully run through our checkpoints and we can move on to the last part. That being said, stop number 3 leads us straight to using equation 4.135, which is the eigenvalues of s squared is equal to h squared s plus 1. Okay, we see that if these are eigenvalues, they come from the eigenequation, which is this statement right here. From here, we see that, well, we have some state s and m, which are not given to us. We're just in some general eigenstate for the spinor that was given in terms of a general normalized spinor. So what we can do is multiply by the bra of the same state Sm, because we want to find the inner product. Doing so, we see that these are nothing but constants, so we can move them outside thanks to linearity and all that other stuff. Seeing here, we don't know what this is yet, but we can move it over to the left-hand side, and that's what we do here. What this represents is the normalized vector, or normalization, for any vector S, or in this case, any state S, not necessarily a vector, it's a matrix. So for any of the states here, this is the normalization of it. That being said, we now can put this down as a normalized expectation and just recondense it to s squared, thus proving that this is h squared h bar squared s times s plus 1. Really, a whole lot of work, but we just need to make sure that the states match to get to this expression, and then we're good to go. Otherwise, it's kind of hard because what if these were primes and they were two different states? Then we'd have to be careful on how to use this. But nonetheless, we can now use this to simplify down and compare results. What we know about this is that in this particular section, we're dealing with spin 1/2 particles, and that's where the Pauli spin matrices come from. And with this, we know that if spin equals 1/2, s equals 1/2. So we simply have to plug this in. And when we do so, we get 1/2 times 3/2, which gives us the 3/4 h bar squared that we see here. Compare this to what we found with the other square expectations. We see that if we add h bar squared over 4 3 times, we do indeed get back to 3 h bar squared over 4. So very nice to see that conclude in such a tight manner. Again, this problem was not necessarily difficult, it was pretty mechanical, but it lays the foundation for seeing some of the things and how they will fit together later. So keep in mind, this is just a hindsight problem. Yeah, not too bad, and we'll move on to the concluding remarks. So thank you for watching. It definitely is helpful, even though I've been slacking with all my travel and work recently. I appreciate the continued support. But as you know, in this question, we covered the expectation values, both the first power and the squared. And of course, we compared the squares in terms of adding them together to verify that this is the same as the eigenvalues we found from the algebraic expressions. So nice to see that things come together. Again, the eigenvalue equations and systems tend to be the bane of your existence as you continue in the space of physics. So be on the lookout. You'll see it everywhere now. Again, I need to emphasize a big thank you again to the supporters of this channel. You make this possible. Please consider supporting this channel by subscribing and sharing this curiosity. If you'd like to give more, please consider joining the Patreon as these members have. Looking forward to doing some collaborative projects this year with them because with the whole tech fest going on right now, there's plenty to be curious about. Books, notes, and other reference materials are found below. If you have any questions, please feel free to reach out. This stuff is really fun and certainly captivating. But that being said, there's certainly more than one way to approach this subject. There is no the way, there are several ways, and whatever might work best for you is what needs to be explored. As always, thank you for watching, and until next time, stay curious.